The last circuit we're going to talk about is an LRC circuit. That's when we have an inductor, resistor, and a capacitor all in the same circuit together. Now keep in mind, most circuits in reality have a certain amount of internal resistance. So as I said before, there's no such thing as a true LC circuit. Everything's going to have a little bit of resistance to it. So we're going to talk about that type of behavior. So when we start with an LC circuit, of course, we're going to charge our capacitor and then put it in the circuit with the resistor and the inductor. So once we do that, of course, the capacitor starts to discharge. And so once again, we get this transfer of energy from the electric field of the capacitor to the magnetic field of the inductor, just like we did before with the LC circuit. However, the difference is that the energy is then dissipated through the resistor. And anytime you hear the word resistor, you should think energy loss. So we're losing a certain amount of energy as it goes across the resistor. So remember, the rate at which energy lost is calculated by power. Power is I squared R when we talk about dissipation of energy. And so the amount of energy that returns to the capacitor is less than the original amount. Now, depending upon the amount of resistance in the resistor dictates how that oscillation between the capacitor and the inductor will go and how long it actually oscillates for. So if the resistance is very high, then you run into an issue where it never really oscillates. The energy just dissipates through the resistor and you don't really get another cycle. But we're going to talk about realms where R is relatively small so that we can actually see a dissipation or a reduction in the amount of oscillation. So I've written here a formula here. It actually looks very similar to the one we learned for the LC circuit, where Q equals the maximum charge cosine omega t plus phi. So what's different here is we calculate what the angular frequency is slightly different by an omega prime term. So it has the 1 over LC in it, but there's a factor that includes the resistor. What's also different is this exponential term out front. And what that exponential term does, and it's a minus sign there, so it's an exponential decay, it essentially decays what the amplitude or maximum current or maximum charge will be as time progresses. So as t gets bigger, the exponential term, which is really, since it's a minus sign, 1 over that, gets bigger. So you're dividing by a bigger sign, and this maximum Q actually gets smaller. So you're going to get, with every oscillation, the initial charge is going to be smaller and smaller, so you're going to have less energy stored in the capacitor that's going to dissipate, or that's going to discharge into the inductor again. So this leads to an exponential decay in the amount of maximum charge that you can actually have. Alright, so what I have here is a circuit. We have a resistor up here, we have an inductor, and we have a capacitor. And then I put an ammeter in here. Now right now I have the resistance set. Let's double check. Change resistance at 0 ohms. So this is really an LC circuit. So if I hit play down here, we see the current flowing, and you can actually see the electrons or electron holes, depending upon your preference, flowing. But then you'll notice that the current starts to decrease, and then we see the charges go the other direction, and the current begins to increase again. So you're seeing this oscillation back and forth, where you're seeing the current increase and decrease, and you see a switch in direction of the flow. Alright, so now what I'm going to do is I'm going to change the resistance of the resistor. And so, let's see, let's use the little bar here and increase it up to 25 ohms. Now let's see what happens to the oscillation. And you can see it happening relatively quickly, where the maximum current that we can actually get is actually decreasing, and the electrons aren't moving as fast because of that. And eventually it comes to a stop. Oh, we're going to increase a little bit, very slowly. So you can see here very dramatically the effect of having that resistor in the circuit, how it affects the movement of the charge between the capacitor and the inductor, and thus how it affects the current in the circuit.